All right, we'll go ahead and get started. Sorry about that. I had Zoom problems here, so can the people on Zoom hear me and see the slide?
Yes.
Okay, thanks. So what we're going to do today is we'll finish up chapter 15 and then start on chapter 16. I want to remind everyone that on Thursday of this week, we'll have a quiz on chapter 15. So, okay, so when we left off last week, we were about to start this part about calculating equilibrium concentrations. And remember, we talked about kind of setting up similar problems where we make the box and fill in the information that we know, and then go through and using that one slide that I talked about probably 20 times, use that kind of logic to then fill in the blanks, and then we can get to where we can set up an equilibrium expression and solve whatever variable we're looking for. So in this case, where you know the equilibrium constant, and you can take some information about equilibrium concentrations, equilibrium constant, all that, and do some of these calculations. For this type of problem, the one change versus what we did last week is that the change in concentration will just be a variable. And we were about to start on that, and I said, you know, that's going to take a little bit longer to go through, so I wanted to wait till we had the full class period. So that's what we're going to do here to start off, is do an example of where we don't have an actual number for the change in concentration. We're going to generate variables, and the variables are based on the stoichiometry of the chemical equation, so the reaction equation. So in this example, we're saying we have a 1 liter flask, and in it, it has 1 mole of H2 and 2 moles of I2. And then we're given what the equilibrium constant is, and we're told that's 50.5. And so we also see that we have the balanced chemical equation. And the things to note there are that when we look at the coefficients on that equation, we see that H2 and I2 have coefficients of 1, and HI has a coefficient of 2. So we know that tells us that for each mole of H2 or I2 that react will form 2 moles of HI. So at the bottom here is a table that should look familiar. That's similar to the table that we did on the problem last week. And so we have our initial concentration, and I just want to point out that that's molarity. So since we're a 1 liter flask, we don't have to do any math on that, but if it was a different volume, then we would have to do some division to get that in moles per liter, okay? So 1 molar and 2 molar for our concentrations of H2 and I2. And then since we're starting, we don't have any HI, so we put a 0 in there. Well, what's the change that's going to take place? This is where that stoichiometry on the reaction comes into play. 1 mole of H2, 1 mole of I2 gives us 2 moles of HI. So if we define an amount as X, then we'll have minus X and minus X for the H2 and I2 changes, twice that amount because of the stoichiometry once again for HI. And since on the left-hand side, those are the reactants, so it's a negative value. And on the right-hand side, the products, that's a positive value because that's what we're forming. So that concentration's increasing. So then to get our equilibrium concentrations, it would simply be the initial, and then we're losing X in each of the reactant situations. So we get 1.0 minus X and 2.0 minus X. And then the equilibrium concentration for the product, the HI, would be 2X. So before, when we did this type of table, we had a lot of numbers in there. So the math was a little more straightforward. In this case, if we think of setting up our equilibrium expression, so our constant equals HI squared divided by H2 concentration times I2 concentration. And remember that expression came from our reaction equation and then using the coefficients. And remember, we said it's products over reactants, and then each of those concentrations is raised to the exponent of whatever that coefficient is. So that's why we have 2x squared in this case. So we plug in those values and we have 2x squared divided by 1 minus x times 2 minus x. And then that's equal to what that equilibrium constant was, the 50.5. And so then we would need to solve for what x is. Okay, so before we get to that point, hopefully everyone remembers how to do the math, especially in the denominator. Okay, so to do this type of multiplication, remember you take 1 times 2, and then 1 times the minus x. You take the minus x times 2, and the minus x times the minus x. And then you'd combine all those terms, okay? So on one of the homework problems, I have it worked out in more detail, and we'll go through that. But if this type of algebra, if you're a little rusty on it, make sure you do some of the homework problems so you refresh your memory on how to do that, okay? The other thing about this is you're going to have to use the quadratic equation to solve this problem. And this is what I was mentioning the other day. In Appendix A3 in the textbook, they talk a little bit about the quadratic equation. You know, that's not something you probably use every day, so you may have to refresh your memory on it. That's fine. But just to remind you of how that works is, it's based on the concept of having some value times x squared plus some value times x plus another value equals 0. And with that set up, where A, B, and C then can be plugged into this formula here on the right, the x equals minus b plus or minus square root of b squared minus 4ac divided by 2a. So the a, b, and c in that formula I just said are these coefficients, these values in the ax squared plus bx plus c equals 0. And so on the problem that we're working right now, if you went ahead and did the math correctly on this 2x squared divided by 1 minus x times 2 minus x, then you would get this formula here, 46.5 x squared minus 151.5x plus 101 equals 0. And in this case, the 46.5 would equal that a value above, 151.5 would equal the b value, and 101 would equal the c value. So you would then plug those values into the x equals minus b plus or minus square root of b squared minus 4ac over 2a. You would plug those in, and then you would solve it. And the other thing, hopefully you remember, that's kind of odd about the quadratic equation is you always get two answers. So you have to make decisions on that. And you get two answers because of its plus minus term, okay? So basically what the plus minus term means is you work the problem out once where that value is plus, and you work it out again with that value being negative. And that's why you get the two numbers. The thing about the two numbers is almost always one of them doesn't make any sense. And so here we get values of 2.32 and 0.95. If we go back to our original table, our initial concentrations were 1 and 2, and then we're going to be subtracting that X value from it. So if those initial values are 1 and 2, and we're saying the answer from the quadratic is either 2.32 or 0.935, one of those doesn't make any sense to me. Which one do you think doesn't make sense? Yeah, 2.32. Why is that?
That's more than we can subtract from the concentration.
Yeah, it's more than what we started with, right? So if, once again, we go back here, started with 1 for the H2 and 2 for the I2, we can't lose more than we started with, right? So from just a common sense type of perspective, that tells us that even though solving the quadratic equation gave us two values, the 2.321 doesn't really make any sense from just a logic, chemistry, whatever you want to call it, point of view. And so that means the 0.0935 is the value we're going to use. So we would go ahead then and subtract that 0.935 from 1 to get our concentration of H2, and we'd subtract it from 2 to get our concentration of I2, and then we would put it into our HI equation to get that, 2 times that, and that's how we would solve to get our molarity values. So the takeaway from this problem is the kind of thought process and logic is similar to what we talked about when we did this kind of box presentation in terms of trying to find equilibrium concentrations or equilibrium constants, things like that. That part really doesn't change. What changed was based on the information that we had to use the X variable to represent the losses or gains that we had. And then that translates into needing to use the quadratic equation to solve the problem to find out what X is. And then finally, we had to think about it a little bit and decide which of those values the quadratic equation gave us really from a logic point of view made sense. Any questions about this? Like I said, we'll go through another one in a little more detail at the end of the chapter when we look at some homework problems. But definitely make sure you try a couple of these in homework for 2 reasons. One is so that you're clear on how to set the stuff up. And then secondly, that you're clear on how to do the calculations. Because I'll tell you, doing the calculations down in this quadratic equation, a lot of opportunities to mess up with your calculator, okay? So make sure that you're comfortable doing that calculation and, just comfortable doing the mechanics of it. Okay. We're going to move on to something called Le Chatelier's principle. And what it says is that if a system at equilibrium is disturbed by a change in either temperature, pressure, or concentration, the system shifts the equilibrium to counteract that effect. So all this is saying is you have one of these changes to the system is going to react to try and get back to how it was before. Because remember, we said that equilibrium is just a term to describe how the system wants to be, okay? And so if something happens to disrupt it, the system's going to react to try and get back to that state of how it likes to be. It's no different than anything else. If something happens to you and you get upset, what does someone say to you? Calm down. It's going to be okay. They're trying to get you back to equilibrium. It's the same for chemical systems, okay? Something happens. In this case, we're saying it can be temperature, pressure, concentration of one of the components. And when we say concentration of one of the components, we are talking about not just reactants, but also products. But one of those things gets changed. The system doesn't like it. The system has to calm down. It has to try and do something to get back to that more normal state that it wants to be at. So we're going to talk a little bit about how things react when some of these changes occur. So the first one let's take a look at is concentration. So if the system's in equilibrium, okay, we're going along, we got our reactants, we got our products, those concentrations have reached equilibrium. And then now you add one of the reactants. You add some more reactants. Well, what's going to happen? Think of it as you've got too much on the reactant side, so you're going to form more products to get that balance back. If you add more products to it, you increase that concentration, well, then that side of the reaction is out of whack. And so it's going to go back the other way and more reactants are then going to form. And so here, down in the picture at the bottom of the slide, there's just kind of a graphical representation, in this case, where hydrogen was added. And so then you see a reaction to that in terms of the other components responding in order to get everything balanced back out. Because remember, in terms of concentration, when we write that equilibrium expression, it's products over reactants equals the constant. So the individual numbers can change within that expression for the products and reactant concentrations, but it's the ratio that has to remain the same, okay? Because the constant is a constant, so it's not changing. So those concentrations, if one of them changes, then the other concentrations will vary in order to get things back to where they want, where it wants to be, and establish that equilibrium. If we think about gases and we think about changing the pressure or the volume. So higher volume or lower pressure, so that's the same thing, right? Lower pressure, things expand. They expand, that's higher volume. Favors the side of the equation with more moles and vice versa. So once again, you're trying to balance out, you're basically balancing out the concentration stuff. So remember, we talked last week about how we can write some of those expressions for pressure. But pressure, just like concentration for liquid products, it's products over reactants in the equation. So a similar idea there with the pressure. And then finally, temperature. Temperature is kind of interesting, I think, when you think about it, because in equilibrium, it does matter if it's an endothermic or exothermic process. And the reason why that is adding temperature, if you add temperature in, you can almost think of it as a reactant. And so if it's an endothermic reaction and you have heat involved, adding heat, what does that do? That's gonna drive it towards the products. Because if it's an endothermic reaction, you need energy, you need heat going in to make the reaction to go. And so in that case, if it's an endothermic reaction, putting heat into it drives the reaction towards the products. If it's an exothermic reaction, heat is one of the products, right? Because we say exothermic reactions those reactions go, one of the things that happens in addition to forming whatever molecules it forms is it gives off heat. So if you add heat to that system, it doesn't make the reaction go because the reaction doesn't need the heat to go, but that heat shows up as additional product. In that case, once again, that product over reactant thing is out of whack. And so it's going to drive it back to the reactants. So like I said, to me, the temperature one, the adding heat one is kind of interesting because that does depend on what kind of reaction you have. The other two that we talked about, the pressure volume one for gases and the concentration one for liquids, that doesn't matter if it's exothermic or endothermic. Change in temperature, it does. And once again, that's because if it's an endothermic reaction, if we put heat into the system, that's encouraging the reaction is how I think of it. If it's an exothermic, well, that's giving us more products. And so it kind of pushes the reaction back towards the reactants. We've talked in the past about, any questions about that before I go on? Okay, we've talked in the past about catalysts. And what did we say the purpose of a catalyst was? We said it was to lower that activation energy so that the reaction could proceed more easily. Didn't need as much energy for the reaction to proceed. Well, the interesting thing about catalysts is that activation energy works both ways, okay? So if you think of down here at the bottom of the slide, we have our diagram of the activation energy and the catalyst lowering that. Well, it doesn't just work one way. If you lower that activation energy going one way and it's an equilibrium reaction, you've lowered it going it back the other way. So what that means is you can get to equilibrium more quickly, but it doesn't change the composition, okay? The ratio and all that stays the same. It's just the time happens more quickly. And the other thing about the activation energy, if you lower that, then usually you can get to equilibrium at a lower temperature than you would without that catalyst. So let's take a look at a couple of these homework problems. So the first one is 1513. And in this one, we're told that we have a gas phase reactions of A to B and B to A, and we're given rate constants for these. And then we want to calculate the value of the equilibrium constant for A to B. So if we've got the rate constants for the two, so basically we're saying it's the rate constant for the forward reaction and then the rate constant for the reverse reaction. To form that equilibrium constant, to calculate that, we simply take the forward one versus the reverse one and divide those. And if we do that, we get a value of 8.1 times 10 to the minus 3. Then in part B, it wants to know which is greater at equilibrium, partial pressure of A or the partial pressure of B. So if we have A going to B, and we want to write what that equilibrium expression is, it would be the concentration of B, our product, divided by the concentration of A, our reactant. Well, we said before, when we calculated in part A, what that value is, what that equilibrium constant is, we said it was 8.1 times 10 to the minus 3. So what that's telling us, A must be a much bigger number than B, because if they were equal, it would be 1, right? 1 over 1 is 1. So if the B concentration and A concentration were exactly equal, it would be a value of 1. Well, 8.1 times 10 to the minus 3 is quite a bit lower than 1. So for that to be lower than 1, the A concentration has got to be a bigger number than the B concentration. And so that tells us that in this situation, A is bigger than B. It's that simple. And that's to be honest, that's really one of the key things to remember when you're thinking about this equilibrium stuff. It all comes back to this expression, like here we have B over A, which is as simple as it gets, but really they're all the same. It's products over reactants. We need to take into account the stoichiometry of the balanced equation. So sometimes you square something or something like that. But it's still, what we're looking at is products over reactants, and based on what that ratio is, that really tells us where the equilibrium is. Is it more favored towards the reactants or more favored to the products? Because it's a simple relationship there. So if you can remember that, I think you'll be in pretty good shape. Okay, next one, 15. Okay, in this one, they want us to write rate expressions for a bunch of different reactions. So we'll go through a few of these. So here we have 3NO going to N2O plus NO2. And then they also want to know, is it a homogeneous or heterogeneous reaction? So as I said before, to write these equilibrium expressions, we look at that balanced chemical equation and we put the products over the reactants. And then if any of them have a coefficient in front, then that term gets raised to that power. So in this case, N2O and NO2 are our products rather. So those concentrations go in the numerator. NO is our reactant. We only have one in this case. And so that goes in the denominator. Then we go and we look back to see what coefficients are there from our balanced chemical equation. And we see that the NO is the only one that has a coefficient in front, and it has a 3. So we take that NO concentration to the third power. And that's our rate equation. Our equilibrium expression. It's homogeneous. Why? Why is it homogeneous?
In the same phase.
They're on the same phase. In this case, we're told they're all gases. And so the homogeneous, heterogeneous should be pretty straightforward for you. You just look at the little terms next to it in the parentheses. If they're all gas or all liquid or all whatever, then you know that it's homogeneous. The most common thing when it's not homogeneous is one of them is a solid. That's the most common. The next one, CH4 plus 2H2S going to CS2 plus 4H2. Once again, we're going to do the same thing of looking at the products, in this case CS2 and H2, putting those concentrations in the numerator. We look at our reactants, CH4 and H2S, put those concentrations in the denominator, and then we go and see, do we have any coefficients on the formula? In this case, we've got a couple of them. We've got 4 in front of the H2, so we're going to raise the H2 concentration to the 4th. We have 2 in front of the H2S, so we're going to raise that one to the 2nd. once again, they're all gases, so it's homogeneous. The next two are pretty similar. You guys can look at those. Let's go down to F. That one's a little bit, well, let's do E first. Let's do E first and then we'll do F. So E, we have silver Ag plus zinc plus 2 going to 2Ag plus zinc. A couple things that we have here. If we look at this equilibrium expression, we notice that it's Ag plus squared divided by zinc plus 2 equals the equilibrium constant. Well, I've said over and over that it's products over reactants, but we don't have our zinc product listed. We don't have our silver reactant listed. Why is that?
Because they're pure substances.
Right, they're pure substances. So if it's a pure substance, remember we said if it's a pure substance, then it has a value of 1. If it has a value of 1, it doesn't show up in the expression, okay? So that's why here, and how do we know these are pure? The definition of pure substance was it's a solid of a compound, a single component compound, or it's a pure liquid. And so we know we have two solids here. The zinc in the product has a little S in parentheses by it, and the silver and the reactants has a little S. So that tells us those are solids, and it tells us those are pure substances, so they're not going to show up in the rate equation. Or rather, they keep saying rate equation, in the equilibrium expression. And so that's why those don't show up. It's just the zinc plus 2 and the silver plus values that we're going to have in there. Because we have aqueous and solid material in this, it's now a heterogeneous reaction because we've got two different types of phases, solid and liquid. So remember, if you see that solid, like in this case, we had 2 of them, then those don't show up in the equilibrium expression. All right, let's look at F. So we have water going to H plus OH. Well, take a look at that expression. We have H plus times OH minus equals the equilibrium constant. What the heck's going on there? Why don't we have H2O in the denominator? It's a pure liquid. And how do we know that? You see the little L in parentheses there? That's telling me that that's a pure liquid, essentially, or you can think of a pure liquid, a solvent, however you want to think of it. Notice the H plus and the OH minus have a little AQ, so it's a different designation. So the fact that those designations were different. You see a similar thing on G. We're not going to go through that because it's the same, pretty much the same problem. But that's another example of where, in this case, the H2O doesn't show up in the expression because it would just have a value of 1, and so we don't put that in. The interesting thing also about this is homogeneous. It's all liquid, right? Whereas the E problem, because of the solids and liquids, was heterogeneous. So that idea of writing the rate equation, or rather the equilibrium expression, products over reactants, the only thing you got to really be careful about is if it's a solid or a pure liquid, then that doesn't show up in it. Any questions about any of these things we've gone over so far? Okay. Let's look at 1521. So in 1521, we're given an equilibrium constant for this reaction, PCl3 plus Cl2 going to PCl5. And we want to find the equilibrium pressure constant. So if you recall, there was a relationship between K sub P and K sub C, and that is K sub P equals K sub C times RT raised to the delta N. And that delta N is the moles of gaseous product minus moles of gaseous reactants. Okay, that R is the gas constant, T is the temperature in Kelvin. So we go back to our balanced equation was PCl3 plus Cl2 going to PCl5. And what we see there, we have 1 mole of gaseous product, 2 moles of gaseous reactants there. So we can solve our delta N, so it'd be 1 minus 1 plus 1 for a value of -1. Our temperature, we're told, is 500 K, so that's units are fine. And so then it's just a matter of plugging those values in to our formula. So our K sub C, we were told, was 0.042. Our gas constant, 0.08206, and then that 500 Kelvin. We take that 0.08206 times 500. We take that to the -1 power, so in other words, 1 over it, and then times 0.042. And if we do that, we get a value of 1.02 times 10 to the -3. So the key to doing this type of problem is remembering this relationship between K sub P and K sub C, remembering how to calculate delta N, so moles of gaseous product minus moles of gaseous reactants, getting that relationship, that molar relationship of the gases from our balanced equation. Okay, so this is how we knew it was 1 mole of products, 2 moles of reactants. And then making sure our units are all right, making sure our temperatures in Kelvin, stuff like that. And then plugging it in to the equation and then doing the math. So once again, make sure you're familiar with this type of formula and how to apply it to go between K sub C and K sub P. Okay, so now this one, number 31, I think this is the quadratic one. Let me see. Oh, no, we're not there yet. Okay. So in 31, we're given the reaction to produce methanol. So CO plus 2H2 going to CH3OH. And we're told it's a 2-liter vessel, and we're given some mole values for methanol, which is CH3OH. We're given the CO value and the H2 value. And they simply want to calculate the equilibrium constant. So we have our balanced chemical equation up here. CO plus 2H2 going to CH3OH. So we can write that equilibrium expression, products over reactants, like we did before. So it's the methanol concentration divided by the CO concentration times the H2 concentration. Because the H2 in the balanced chemical equation had a coefficient of 2, we have to square that term. And so then it's simply a matter of plugging in the concentrations for those 3 components. Well, we were given the moles, 0.0406 moles of methanol, 0.170 moles of carbon monoxide, and 0.302 of hydrogen. But we're in a 2-liter vessel, so we can't just plug the mole value in. Because remember, we said when we write these equilibrium expressions, it's molar, so moles per liter. So we just simply, it's a 2-liter container, so we have to divide each of these by 2 to get the molar values. And if we do that, then the CH3OH is 0.0201, 0.085 for the CO, and 0.151 for the H2. So now we've got our concentrations in units of molarity. We've written our equilibrium expression correctly. And so then it's a matter of just plugging in those concentration numbers into our equilibrium expression and then solving for that, okay? So once again, the key things to something like this is remembering it's products over reactants, remembering that if there's a coefficient out in front of something, then that concentration has to get raised to that power. And then finally, remembering that it's not moles that we're working in, it's molarity, so moles per liter. So in this case, where we didn't have a 1-liter vessel, we had to do a little bit of math to convert the moles into molarity. Okay, let's look at 4.3. So in 4.3, we're told we have a balanced reaction that we're given, COCl2 going to CO plus Cl2. We're given the equilibrium constant value, and then we're asked, are these following mixtures at equilibrium or not? And if not, what's going to happen? What direction are they going to go? So this goes back to, remember we talked about calculating the Q value, and Q was just another calculation. It's really the same calculation as an equilibrium constant calculation, except it's giving us what the value is at that point in time. And by comparing that value to what the known equilibrium constant is, we can tell, does the reaction need to move towards the products to establish equilibrium, or does it need to move towards the reactants to establish equilibrium? So we go ahead and write our equilibrium expression. So that's the CO times the Cl2 concentration divided by the Cl2 concentration. No coefficients there in the balanced equation except for 1, so we don't have to have any exponents on any of those. And then that's equal to that equilibrium constant that we were given, the 2.19 times 10 to the minus 10. So for our Q value, we're just going to take that expression, that equilibrium constant expression, we're going to plug in the values that were given for this point in time. And so on the first one, the CO is 3.3 times 10 to the minus 6. The Cl2 is 6.62 times 10 to the minus 6. The COCl2 is 2 times 10 to the minus 3rd. We plug all those in, and we get 1.09 times 10 to the minus 8. So wonderful. What do we do with that? Well, we take that value and we compare it back to what we were told is the known equilibrium constant. And that's the 2.19 times 10 to the minus 10. Well, the number that's 10 to the minus 8th versus the number that's 10 to the minus 10, which is bigger? 10 to the minus 8th. And so if that number is bigger, that means that I have more in the numerator, right? The numerator is products. So if I have more products than I want, that equilibrium has got to get pushed back towards the reactant side, okay? And so that tells us in this first case, if those concentrations, if we were to kind of monitor that reaction for a little bit of time, what we'd see is, we'd see the products decreasing and the reactant increasing. In B, we do the exact same calculation, just using the new numbers that were given for those concentrations at that time. We go ahead and do that, and we get 5.5 times 10 to the minus 12. Well, 10 to the minus 12 compared to 10 to the minus 10th, that tells me that this is too small of a number, okay? If it's too small, that means the denominator is too big. The denominator, once again, we're products over reactants, the denominator is reactants. So it tells me I have too much reactant, not enough product. So that reaction is going to move in the forward direction. The reactants are going to react to form more product to get us to that 2.19 times 10 to the minus 10 value. So this is the benefit of the Q calculation. It's simply allowing us to calculate this ratio of products to reactants at some point in time and allow us to compare it to the equilibrium constant and see which way that reaction would like to proceed. Form more product or go back and have more reactants. And once again, as I said earlier, if you can just remember this, all we're saying here is products over reactants, products in the numerator, reactants in the denominator. It really is that. If you can break it down that basic, that'll be really helpful, I think. The third one, given concentrations again, we plug those in and look at that. We get 2.19 times 10 to the minus 10. We look at that number, we compare it back to our equilibrium constant, they're the same. So what that's telling us is these concentrations are equilibrium concentrations. And that's because when we did this calculation using the numbers that we were given at that point in time, we actually got our equilibrium constant value. And so that tells us the reaction's good to go where it is. It's the concentrations are where they need to be. So any questions on how you use that Q value to tell what the reaction is going to do? Is it going to go to products or reactants? Okay. And just to remind everyone, as you study for the quiz, all the homework answers are posted, so you can certainly look it up and if you get stuck on something. Okay, let's do 47. So in 1547, we're told, in 1547, we're told that we have Br2 going to 2Br. We're giving the equilibrium constant. We're told we have 0.2 liter vessel. And we're told how much Br2 we began with. And we want to find what's the mass of Br. Okay, so if we look at this one, a good place to start is always write that equilibrium expression. You know, that's always useful to do. This one is pretty simple because it's just two things in it. They're both gases, so they're good. Br over Br2, we need to square that Br concentration because of the 2 coefficient in the balanced equation. We're told we have 0.2 liters as our vessel, and we're told we have 0.245 grams of Br2. So we know that when we're talking about equilibrium expressions, we want to be in molarity when we're talking about how much stuff we have with the units. So we can change that 0.245 grams into moles. And then based using the 0.2 liters, we can change it into molarity. But first we need to calculate the molecular weight of Br2. So we look up the atomic weight of bromine, 79.9, and we get the value of 159.8 grams per mole. So we convert our 2.245 grams of Br2 into moles of Br2 using that molecular weight. Divide those moles by 0.2 liters, and we get a concentration for Br2 of 7.7 times 10 to the minus 3 molar. We had been given the equilibrium constant. We now have a concentration for Br2. So we can plug those two values into that equilibrium expression that we wrote in the beginning. And so now we have 1.04 times 10 to the minus 3 equals the concentration of Br squared divided by our 7.7 times 10 to the minus 3 molar value for Br2. We go ahead and solve this, and we get 2.83 times 10 to the minus 3 molar as our Br concentration. Except, remember we said we wanted grams, okay? So what we have to do is we have to take this 2.83 times 10 to the minus 3 molar, so that's moles per liter of Br, and convert it into grams. Well, the first thing we do is we use our 0.2 liter value and multiply that by it to cancel out our liters. Then we use the atomic weight of Br, bromine, 79.9, to convert the moles into grams. And then that leaves us with just grams of bromine. So we use the size of the vessel, the liters. So liters times moles per liter, liters units cancel. So now we just have moles as a unit. We have moles, grams divided by mole, that's the atomic weight of bromine. That cancels out the moles units and leaves us with just grams. So this one was a little different. This one was the setting up the problem, solving for that molar concentration. That's the same as what we've been doing on a lot of these. So that part shouldn't have been new to you. Well, a couple of things that were new were we didn't have a nice 1 liter vessel. We weren't given it in moles. So we had to do some manipulation there to change grams into moles and then take into account a non-1 liter vessel concentration to get a molar concentration. Then after we did all that work and found out our concentration of, in this case, Br, they wanted it in grams. So then we had to kind of go backwards again from that moles per liter to grams. And that's where we used that volume. We use, in this case, an atomic weight to get that from a moles per liter concentration to a number of grams. So a couple of little different twists there on the basic stuff that we've been doing. Okay, now here's where we're going to do another one that uses a quadratic equation, but I have the math worked out in a little bit more detail just to make sure everyone can see it and be comfortable with it. And like I said, this is posted, so if I'm going through it, if you have a question, certainly stop me. But if later on you're looking at it and you're a little confused, hopefully this is a little more detail and will help you. Okay, so in 1552, it's that Br2 plus Cl2 reaction going to 2BrCl, and we're given the equilibrium constant. We're given number of moles of Br2 and Cl2, and we're told it's a 3 liter container, and we want to know the equilibrium concentrations for these 3 components in our reaction. So first thing, like I said, I always like to do is write that equilibrium expression. So BR2, BrCl2, that's the product. The reactants BR2Cl2. The BrCl2 has 2 in the stoichiometry, which we can't really see because of this thing up here. So let me move that. So we see on the top of the page, the reaction, balanced chemical reaction. And that from that chemical equation, we know that BrCl2 has to be squared. And that equals our value of 7. That equals our equilibrium constant. I have a question for you. What's the units on the equilibrium constant? Any guesses? So sometimes I don't always put the units on, and that's not good that I don't do that. But in this case, with equilibrium constant, there are no units because everything cancels. Because what are the units in our equation? It's moles per liter. So in the numerator there, we have moles per liter squared. The denominator, you have moles per liter times moles per liter. So that'd be moles per liter squared. Moles per liter squared divided by moles per liter squared cancels out. That's how the rate constants are, and the equilibrium constant is. That's why you don't see any units on any of them. So this isn't me being deficient for once. It's actually correct. There is no unit. Okay. Hopefully the next thing below that equilibrium expression looks familiar. That's the little box setup that I've been strongly encouraging you to get in the habit of setting up for these types of problems. And so we have on the left-hand side of the table, initial, the change, the equilibrium. Across the top, we have the 2 reactants and then the product. And we have what we start out with. Okay, so 0.083, 0.18, and then 0 for the BlCl2. But wait a second, we weren't given 0.083 or 0.18. Where'd those numbers come from? Well, this goes back to our units are molarity, moles per liter. And so for the BR21, for instance, we were told it's 0.25 moles, but it's a 3-liter total. So we have to take that moles and divide it by liters, and that's where the 0.083 value comes from. So that's how we get our molarity, that moles per liter, which is what we need for that equilibrium expression to fill in those concentrations. Same thing for the Cl2. We take that 0.55 moles and divide it by 3 liters to get 0.18 molar. So that's why in our little table up here, we don't have the mole values. We needed moles per liter molarity values. So that's something you always got to check. Do I need to do any math on the moles to get it into a moles per liter concentration? Okay, so we use our stoichiometry from the balanced equation. 1 mole Br2, 1 mole Cl2, 2 moles BrCl, Cl2. And so what do we have? We have minus x, and then 2x of the BrCl. That's the change. Then the equilibrium would be the 0.083 minus x, 0.18 minus x, and then a plus 2x for our product. Okay, so we go ahead and we set up the math. We have our equilibrium constant 7 equals 2x, and that's squared, divided by 0.083 minus x times 0.18 minus x. And we start doing the math. So for me, the first thing I do is I get the denominator out of the bottom. So I take the denominator, 0.083 minus x times 0.018 minus x, multiply each side by that. And so then now I have 7 times 0.083 minus x times 0.18 minus x equals 2x squared. Okay, you certainly don't have to do it this way. I'm just showing you how I do it and how I walk through it. Let me move this thing again here, hold on. So then the next thing I did was I did the math of multiplying 0.083 minus x times 0.018 minus x. And I get all these terms, 0.0149 minus 0.083 x. So that's simply 0.083 times 0.18, that's that first term. And then 0.083 times minus x, that's the next term. Then it's the x times that, 0.18 term. So minus x times that is minus 0.18x. Minus x times minus x is x squared. Combine all that stuff, I get this next one of 0.0149 minus 0.263x plus x squared. So all I did here was add those x terms. Then I go ahead and multiply all that by the 7, get this next one, 0.104 minus 1.84x plus 7x squared equals 4x squared. And then the last thing to do is to go ahead and bring this 4x squared over to the other side. Replace it with 0, and then that makes it 3x squared minus 1.84x plus 0.104. So this is a little more detail, so you can see the exact steps. But what you want is that last form, right? Because remember, we talked about the quadratic equation that ax squared plus bx plus c equals 0. So we wanted to get it into the form where we would have a, b, and c identified. We've done that now. And so we can take those terms and plug them into our quadratic equation. That's the x equals minus b plus or minus square root of b squared minus 4ac over 2a. So we go ahead and start plugging in numbers. So b is minus 1.84. That's minus b, so it becomes a plus 1.84, then the minus 1.84. 4a is 3, c is 0.104. We plug all those in, and if you do the math under the square root sign, you should get 1.46. 6 is the denominator, then 1.84. And then you go ahead and solve. Remember we said you solve it as that plus or minus being plus and that plus or minus being minus. We get two values. Using it as the negative sign, we get 0.0633. Using it as the positive sign, we get 0.550. Well, which one is it? Well, this is where we need to go back and look at our start here. Remember our initial, we had a 0.083 and a 0.18 as initial concentrations. Well, the 0.55 is bigger than those, right? So we can't be starting with a negative concentration in our reaction. So that tells me that the 0.55 value isn't reasonable, and that's not going to be the one to use. So we're going to use the 0.0633. We go back to our table and we subtract that from our two reactants, and then we have 2 times that value to be our product, our BrCO product, and then we finally get to our molarities of things, okay? So I write kind of big when I do these problems, but it took me 2 pages of writing to get to that, okay? So to do this kind of problem, I'll repeat this again, is that when you look at writing all this stuff down, at least for me, I get to where I'm like, geez, why do I have to write all this down? Can I take some shortcuts? It's not worth it because there's just a chance, there's a lot of chances to make a mistake on these problems. And so you just got to kind of grind through it. Once again, use that balanced equation to write your equilibrium expression. Set up the table with initial, change, equilibrium, and put the stuff in. Make sure you got your concentrations in moles per liter, not just moles. And then start working through the math. Make sure you're comfortable for these kind of like algebraic calculations. And then once you get through all that, remember the quadratic equation setup and then what that formula is, and plug the stuff in. Kind of do the calculations, maybe double check it. And then you get to a decision point when you do the plus minus thing of going back and looking at those answers and deciding one of them is probably going to make sense and one of them probably is not going to make sense. Which one is the one that makes sense? The one that makes sense, then that's the one you define as your X. And then you go back to that original stuff in the table. So once again, this minus X plus 2X stuff. And do those subtractions in the equilibrium to get to your final answer. Okay, so any questions about the homework problems? I think that's the last one, yeah. Take a look at those, practice them. I think, as you can imagine, there's a high likelihood something like this is going to be on the quiz, going to be on the exam. So get comfortable with that. I think we're going to stop for now. I just want to remind everyone on Thursday of this week, we'll have a quiz on this chapter. And so we'll start the class, starting at the beginning of the class, first 20 minutes or so with the lecture on the next chapter, chapter 16. And then we'll stop and you'll take the quiz for the remainder of the time period. Any questions before we end for the day? Okay, thanks. And once again, sorry for the Zoom issues in the beginning.